We'll now begin our study of rational functions. A rational function is the quotient of polynomial functions, and we'll denote a rational function as p of x divided by q of x, where p of x and q of x are equal to the following two polynomials. The only other condition that we have for rational functions is that q of x is non-zero. This restriction will actually allow us to define the domain of a rational function, and we say the domain of a rational function is all real numbers where we have that q of x is non-zero. Let's go ahead and look at an example. In this problem, we want to find the domain of f of x, which is given by the rational function 4x divided by 5 times x minus 1 times x minus 5. Again, the domain of a rational function is all real numbers x, such that the denominator is non-zero. So if we find all the points where a function is undefined, then everything else will be the domain. Set the denominator equal to 0. Then solve for each x. Setting x minus 1 equal to 0 and setting x minus 5 equal to 0 gives us either x is equal to 1 or x is equal to 5. And these are going to be the points where our function is undefined. Therefore, the domain is going to be every other number. So drawing our real line, let's go ahead and map these points. First, we have a point at 1, and we have another point at 5, and the domain is going to be everything else. So the blue is an indication of points inside the domain, which means we're going to allow all numbers negative infinity to 1, but not including 1, 1 to 5, but not including either one of these, and then 5 to infinity. Then we go ahead and add our union signs, and we're done. Occasionally, a graph of a rational function will have a hole in it, a single point where the graph is not defined. We call such points a removable discontinuity. On the graph, on the left-hand side, we have an example of a removable discontinuity at this green point. These removable discontinuities are defined on our rational functions as follows. Again, suppose we have a rational function f of x, which is equal to p of x divided by q of x. If the polynomial p of x and the polynomial q of x have a common factor, x minus c, then the graph at x minus c is undefined, and we call the point c comma f of x a removable discontinuity. We also have an alternative definition for a vertical asymptote of a rational function. If q of x has a factor x minus c that's not a factor of p of x, then the line x is equal to c is a vertical asymptote. On the graph here, again, the line x is equal to 0 looks like it would be a vertical asymptote. Let's look at an example where we find the vertical asymptotes and the removable discontinuities of a rational function. To solve this problem, we'll first find the removable discontinuities, then cancel out the common terms, and then find the vertical asymptotes. So to find the removable discontinuities, we need to go ahead and factor the top polynomial and the bottom polynomial. The top polynomial will simplify to be x minus 5 times an x plus 5, and in the bottom polynomial, we can go ahead and take an x out of each term, and we're left with an x squared minus 6x plus 5. Now, factoring this quadratic, we'll get that this is equal to, again, x minus 5 times an x plus 5 divided by x times an x minus 5 times an x minus 1. Now, since we have a common term x minus 5 on bottom and an x minus 5 on top, this means we're going to have a removable discontinuity at x is equal to 5. And the corresponding point then would be 5 comma f evaluated at 5. Plugging 5 into our equation, you should get out that this is going to be equal to the point 5 comma 0. Oops, I made a little bit of a mistake here. Well, we do have a removable discontinuity at x is equal to 5. To find the actual point, we need to go ahead and simplify our rational function. This is going to be equal to x plus 5 divided by x times an x minus 1. Then we need to evaluate f of 5 at this function here. So real quickly, let's go ahead and look at f of 5. This would be equal to 10 divided by 5 times 4. So this would be equal to a 1 divided by 2. And therefore we'll have a removable discontinuity at the point 5, comma 1/2. Now to find the vertical asymptotes, we look at the factors of the bottom that aren't contained as factors on the top. So we have x minus 1 as a factor and just x as a factor. Therefore we'll have vertical asymptotes at x is equal to 1 and x is equal to 0.